Okay, today's topic that we're going to take a look at is current and resistance. Right now, for the most part, the meat of this topic is going to be in the next chapter. But this is sort of like the physics chapter, and then the next chapter is like the engineering chapter. The engineering chapter, I will admit, is a little bit more interesting because you get to actually use devices. We're going to have a lab that we're going to do dealing with chapter 27 as well. This chapter with 26, it gets into a little bit more of current density, and we can take a look at how the electric field affects current density. It's a little bit more of a one-to-one relationship between current density and the electric field than current density than between the electric field and current. And we really don't even get into that all that much anyway. But we're going to take a look at what current is. Then we're going to talk about current density and drift speed. Drift speed is the speed of the electrons as they flow through the circuit. I want you to try to take a guess as to how fast you think the electrons are going to move through a circuit before we actually get into it. Just kind of think in your minds how fast you think an electron moves through a circuit. It's actually fascinating how fast it goes. We're going to talk about resistance and resistivity with Ohm's law. Which we talked about last year. And then we're going to get into power, and that's pretty much it. There's not a lot of meat in this chapter. So without any further ado, let's get started. Okay, so now our first basic idea is with current. Okay, current, I'll define it mathematically. It's just the amount of charge that flows over a period of time. So if you want to make it, put that into the language of mathematics, it would be dq dt. It's basically just a number of charges that pass a point in a given period of time. Right? We don't want to get bogged down in that dq dt. When we get into resistor capacitor circuits, RC circuits, we are going to have to do this in terms of, with calculus and everything like that. For the most part, though, when we're dealing with, for the bulk of 26 and 27, we're not talking about it in terms of calculus. It's just, that's how we describe in mathematics the amount of charge that passes a point in a given period of time. I is current. Okay. Now, why they use I, I'm not sure. I don't really care. The units for I, okay, is going to be a coulomb per second, which we call the ampere. It's not amperage. Okay. It's amps or amperes. One other thing here, by the way, we designate that with a capital A. One other thing here, the coulomb is not the base unit. A coulomb is a very hard unit to measure. Ampere is not a very hard unit to measure. So now, the way that we define the coulomb, 1 coulomb is equal to 1 ampere second. This is how we define the coulomb. We do not define the ampere off the coulomb, we define the coulomb off of the ampere. It's sort of like defining distance by a speed as opposed to defining speed by the distance. Okay? And by the way, we do that. That is something that you can do. If you go on in physics and go for like a master's degree or something like that, you will use your base as speed. You'll make the speed of light your base unit, and then you'll define distance off of that. But anyway, I digress. See, even on video I can digress a little bit. Now, what are the important things that we have with current here? Okay, we're talking about the flowing of charge. We've dealt with that quite a bit last year. But one of the most important things that we're going to come into, and this is the second of Kirchhoff's laws, and we dealt with the first one when we were dealing with capacitors, which was the voltage around the loop had to be 0. Well, this is called his junction rule. And what it says is that the current into a junction has to equal the current out of a junction. Okay? So if I do this, and I have it splitting off here and here, doesn't matter which way they go. If I have, for argument's sake, say 3 amps going in here, and I know that I have 5 amps going out this way, okay, I know how much what the current has to be in here. 3 amps flow in, I have 5 amps flowing out here, there has to be more current coming in over here. This would have to be 2 amps, okay? I didn't know if it flowed in or flowed out beforehand, but I knew that I had 3 amps here flowing in and 5 flowing out, so I needed 2 more flowing in, all right? What I want you to do now, okay, is to take a look at this circuit here, okay? It's actually taken from your book. I want you to calculate the current I here, okay? I have 1 amp that's flowing out of this wire here, 2 amps coming in from here, 3 amps coming in from in here, 2 amps that flow out there, 4 amps that flow in here, 2 amps that go across like that. I want to know what the current is I right there. I want you to pause it for a second, and I'll answer it as soon as you take pause. All right, so now we're back. Hopefully you've paused it. Okay, we're going to take a look at how this current adds up. So now, here and here, going into this right here, I have 2 amps going in, 3 amps going in. I have to have 5 amps going like that. So 5 amps is flowing into this junction right here. Well then, I take a look over here. I have 1 amp that's going out over here, 2 amps that's going out over here. So that's 3 amps flowing out. I have to have 3 amps flowing in. So now, I have 5 amps flowing in, 3 amps going out. It's like the opposite of that over there. I need 2 amps, because there's 5 that go in, 3 go out here, I need another 2 amps going out here. Well, I already have 4 amps going in here, which means that there has to be 6 amps flowing out. So now 6 amps flows into this junction, from here 2 amps flows in here. That means if I get 6 and 2, I've got 8 amps. One thing I would say, pause if you get lost at any particular moment in time as you're going through this, okay? Rewind it, pause as I go through each step to try to figure out what I did, okay? All right, now, current density, okay? We talk about current density is the current per unit area, okay? So now, current density, now the reason why we like to look at this, why physicists like to look at current density, is that it is a vector, okay? We say that, and sometimes, by the way, I'll use little I, sometimes I'll use big I. Big I usually means that it's a constant current. Little I means that it could be a variable current, or it could be anything. I will typically use little I because it could be anything. Capital I is usually just a constant current, okay? I is usually a current that will vary with respect to time, or at least has that freedom to. All right, current density is we define actually current off of current density. We have the it's a vector, which is one reason why physicists like current density. Okay. Now, 2 things that we could do. Remember, current is charge that flows past a certain point through, essentially through a cross section of wire. So this is not going to be current density as in volume density. This is going to be an area density, because we're going to look at how many electrons pass by a given point in a given amount of time. So now we can say that the current is equal to the integral of J dot dA. Okay? Realistically, if we can have a current that is uniform through an area, which is pretty common, okay, or at least within our models, it's very common. It's not perfect, but it works out okay. That means that we can pull out the current from there. And we just wind up with the current is equal to the current density divided by the area. So we times the area. Or we would say that the current density is just the current per unit area. Okay. So if we want to look at units for this, the units for current density, again, I don't know why they use J, is going to be I, which is amps, over area, which is meters squared. Okay. Oh, Mr. Phillips, there's an A here and an A here. This is the equation, this is the unit. Okay. Really, that's all that the book talks about with current density. We get into it a little bit more later on when we start talking about how the electric field affects the current in a resistor. We don't have our stipulation that all the charges are at rest like we did with the last one. So we don't say that the electric field inside of a conductor now is 0. This is true, okay? The electric field equals 0 inside a conductor when it's static, okay, when the charges aren't moving. When we have a current, okay, the electric field doesn't have to be 0. It's usually not. Okay. Drift speed, I'll talk about this quickly. So now, they talk about, well, let's see here, I over QT, NA. Okay, typical drift velocity. So if you do I over A, let's see here, 0.49. Okay. I'm not. Well, all I'm going to really talk about with current density and drift velocity, we have this term drift velocity. Okay, it is a vector again. It's in terms of current. Essentially, the important thing to know is it's very slow. I'm not going to go through the proof. I was just looking at it. It's not even worth the time. Drift velocity is very slow. It's on the order of centimeters per second. I want you to go through and try to prove to yourself that's true. Read up on chapter 26 on page 686 and 687. There's actually some good problems there, but I do want to move on. Okay. So now, resistance and resistivity. Okay, resistance is what a particular resistor has. It's how much it restricts current flow, given a particular potential. Okay. Resistivity is a property of any particular material, like the resistivity of copper. Okay, that's not telling you how much it resists, how much a particular piece of copper resists, but it's a property of any piece of copper. Okay. Now, what resistance is? Okay. Resistance restricts the flow of current. So we say resistance is equal to V, the voltage, divided by I, current. Okay. Again, take a quick look at units. Resistance R, the units of it, is going to be volts per coulomb. So volts per ampere. Okay. You can break that down into base units if you want. That is the ohm. In fact, homework number 1, I want the ohm in base units. And that's the kilogram meter second. So I want you to do it in coulombs. Okay? You can do coulombs or amperes. The ampere is truly the base unit, but coulombs we usually think of a little bit more easily as a base unit. I don't care which one you do. Okay? So now the amount of current that will flow, okay, if we just rearrange, the amount of current that flows is equal to the voltage divided by the resistance. Okay? Now, the resistance is a property of the material. Okay? Excuse me. Resistance is a property of the device. It's not the property of a particular material. Now, it's very important to understand that there's a property called resistivity that's a property of material. Okay? And the book goes through and comes up with this equation essentially. That using kind of more the physics aspects of it as opposed to the engineering aspects. Okay? The electric field is equal to, this is the resistivity. Okay? The electric field is equal to rho times the current density, or we could say that the current density is equal to the electric field divided by rho. Okay? So when you get an electric field set up in a material with particular resistivity, a certain current density will form. Again, that's not really how we go about using it. Okay? They go through a little bit of a proof. Here's the important aspects. A material's resistance, excuse me, a device's resistance is equal to the resistivity of the material times the length of it divided by the area. Okay? This equation makes sense. Let me explain to you why. Okay? This is how much a material will let's say we have A and B. Rho is how much the material tries to restrict current flow. Okay? So the bigger the resistivity, the bigger the resistance. If that makes sense. Okay? I have wire A and wire B. Which one do you think will allow more current to pass? The thick wire or the skinny wire? Okay? Here's the thing. The skinny wire, okay, it's sort of like being in traffic. Do you want 1 lane of traffic or 3 lanes of traffic? Okay? 3 lanes of traffic allows more cars to pass through. Okay? 1 lane of traffic, okay, everybody's trying to, it's like a bottleneck, everybody's trying to get in there. So the bigger the area, the easier it is for current to flow. Okay? The smaller the area, the more it restricts it. Okay? So now, if I have a big area here, resistivity is small. Okay? Allows more current to pass. If I have a small area, okay, this number becomes bigger, resistance becomes bigger, okay, restricts the amount of current that flows. The other thing to think about is like this. If I have a wire here, and I'll call this wire C and wire D. Put them about the same distance apart. Okay, same thickness of wire. Which one of these 2 wires do you think will have a greater resistance? The long one or the short one? Why, yes, the long wire will have a greater resistance. Okay? So the bigger L is, the greater the resistance is. The bigger A is, the smaller the resistance. I'll stop there. I'll make up one more video.